My name is Michael Wong, and along with my colleagues, Maggot Michael and Paul McKenney, who's going to call in from Dublin, I believe, we're kind of the, I guess what you call the Concurrency TS2 editing team. We're also the co-authors of the first two papers that is entering Concurrency TS2. So hopefully through this session, we've had other sessions before, but hopefully through this session, you'll learn some of the specific use cases and how to use these guys. I think that's probably one of the most useful things we can go towards. So I'm going to talk a little bit about the TS2 before I hand it over to my colleague, Maggot. So the way standard works is on the right side, there's this life cycle at which technical specifications can become international standards. We're not going to worry about too much about that, but probably one of the first things you're probably thinking about, isn't there already a concurrency TS? Well, there is. There used to be. Back in about 2014, there was a concurrency TS1, and it had things like improvements to stood future, latches and barriers, and atomic smart pointers. Well, those things progressively entered C++. Futures was the first one. Latches and barrier was in the next iteration. And then atomic smart pointers, we kept monkeying it with. It originally had like the double angle bracket, and then eventually had a single angle bracket with a T. And finally, it now has entered C++ 20. Go to Anthony's talk. I'm sure he'll talk a lot about that. Now it's time to initiate new concurrency TS. So we call it concurrency TS2. The repository is actually already on GitHub, and it started life. The actual document started in about 2021, and we project that it will probably finish around 2023. Now the actual work on it was way before that, about 2016, when we started trying to put this stuff into ISO. And the actual work on these guys have predated that for, I don't know, maybe 10 or 20 years. My colleagues will tell you more about them. So here's the thing. If concurrency TS has these two things called hazard pointers and read copy update, why are we putting it already or trying to put it already into C++ 26? Isn't that the cart before the horse? Well, in a way, this is a bit of a unique situation. The two initial items, of course, are, and there's the link to the GitHub, hazard pointers, which I always call HP, not to be confused with that other HP, and read copy update, or RCU. Now, there's going to be a few other possibilities, like something called snapshot and asymmetric fences, and then usually a few more years of experience would follow that. So if we were to follow the normal life cycle of a concurrency TS, this would probably blow way past C++ 26. Oh, by the way, just as I'm not a fan of TSs anymore. I used to be. I was, in fact, one of the early proponents of TSs way back in 2020. I'll admit that. After years of experience, I feel that these TSs, well, they're useful in some measures, maybe for libraries, probably not that great for languages. That's another story. But they do delay entry into IS. Okay, so why are we putting these two guys into the C++? Because they've been there since 2016. We've been trying to put them in since 2016. So are we rebels? Why not wait? Well, the committee generally agrees. We actually put this motion in front of the SG1, and they generally agree to push it forward even before TS2 is out. And that's partly because we actually already have a lot of experience with these two. So I can't remember. I think it was like February, was it? That it was kind of approved by SG1 to move forward into C++ 26. And there are these two papers that will talk about that. And we worked really hard to keep the interface pretty much the same, okay? We do still have to go through LEWG and LWG. Okay, so read copy update. I'm gonna explain a little bit more about these, but just a status where we are. RCU, there's no change for C++ 26, though there's been massive experience on this in the Linux kernel. Most of the scheduler is using read copy update, and now in the Folly library as well too. And so for after C++ 26, there will be some ideas for additions. Hazard pointers, the transition from the TS to IS is minimal. There's going to be, we're going to omit custom domains, and we're going to omit global cleanup. And there's the interface in red that you can see where we're omitting it. Omitting global cleanup actually is pretty cool in that it enables what's called synchronous reclamation. See Maggot's talk from CppCon 2021 on that. And so the theme of this TS is is a lot more about lock-free programming, and specifically more about what's called deferred reclamation. So what is it? We already know that there's going to be at least 2 low-level APIs in it. There's going to be maybe 1 high-level API called snapshot, which is also deferred reclamation in it. So what is deferred reclamation, and why is it important? Okay, it is basically Heisenberg's uncertainty principle married with Schrodinger's cat in a lock-free algorithm. I know it sounds pretty cool, so you gotta really think about this. Here's what the big idea is about. You have readers access data while holding a reader log or having the data that's protected, and you guarantee that the data will remain live while the lock is held or the data is protected. Now, one or more updaters is going to update the data by replacing it with newly allocated data, and all the subsequent readers will see the new value. All the old value, though, is not destroyed until all the reader access have released their locks. Here's where you can have 2 views of Schrodinger's cat, one that's alive and one that's dead. Hence that's why the picture. So the benefit for this is that the readers never block the updater or other readers. The updaters never block the readers. So what you pay is the updates have some extra cost, but it's very small. And of course, they also need they need allocation because there's going to be new value construction. And it's pretty much okay if the updates are pretty rare, which is a fairly interesting situation that comes up fairly frequently. All right, so let's look at an example because I think that might help. Again, let's keep with the Heisenberg uncertainty principle theme and Schrodinger's cat. So Schrodinger wants to construct an in-memory database for the animals in his zoo. They might record things like the birth results in insertions, deaths in deletions. Queries from those interested in Schrodinger's animals might come in, and there might be lots of short-lived animals, such as mice, because they have a high update rate. And there's great interest in whether Schrodinger's cat is still alive, probably from the mice. So there's a simple approach, which is a chain hash table with per bucket locking, okay? And the question, of course, is, you might be holding a lock. Is this going to prevent the cat from dying? Well, fortunately, Heisenberg has taught Schrodinger a few things about how to cope with these uncertainties. It turns out that the delay in detecting the cat's passing permits us to use something called synchronization via procrastination. This is something personally I love a lot because procrastination is my middle name. After all, given that the 2 veterinarians might pronounce the death of the cat separately in different times, they might even be as far apart as 34 seconds, a few additional milliseconds of software procrastination is perfectly acceptable. In fact, Schrodinger's design goes further by actually exploiting the ambiguity and the uncertainty. He does this by basically refusing to require that queries, insertions, and deletions be fully ordered. And as we're going to see, this design choice will give very high-speed queries. So this idea of trading uncertainty for performance and scalability in life is actually quite common. A common problem in parallel programming is acquiring a lock, and while holding the lock, compute some property of the data that's protected by that lock. Now, suppose that this algorithm uses some common idiom that makes a decision while holding a lock, and then relying on that decision after releasing the lock. Well, this algorithm, in fact, is relying on obsolete information because some other CPU might have acquired that lock and changed the data on which that decision was based. Network packets, for instance, often have this thing. So what you would do then after that is you would release the log, of course, and you would use that computed data. So this is the point. So there actually turns out there's several approaches to solve this problem. And we're going to do a quick look at each of these approaches. Not deeply, of course, but it turns out that you could use read-or-write lock. You could use reference count. You can use what we're going to talk about in Concurrency TS2, RCU, and hazard pointer. All right. So here's how we do it. Here's a simple solution for Schrodinger's zoo. And that is to place a reference counter in each animal's data element within a hash table, with collisions handled by chaining, of course. So the readers atomically increment the reference before accessing an animal's data element, and atomically decrement it afterwards. Now, this provides synchronization only between the readers and the updaters. The updaters has to synchronize among themselves using mechanisms like locking, non-blocking synchronization, or even transactional memory. And if you guys know my history, you guys know how much I used to love transactional memory. So this is the idea going forward with these, and this is demonstrating the RCU case, and this is the idea of deferred removal using reference count. Okay, so here's how it works. There are 4 states, and I've illustrated with the diagram here. This is the process of removing the data element corresponding to Schrodinger's poor cat here. Okay, the initial state 1 on the far left shows one chain of the hash table representing Schrodinger's cat, boa, cat, and GNU. Is that how I pronounce it? Is it GNU? As in, so, and you can see that I've colored them red, okay? So any number of readers might be referencing these data elements. Therefore, updates has to be carried out carefully, okay, to avoid disturbing these readers. Now, as we transition to state 2, the updater stores a pointer to the GNU's data element in the next pointer of the boa element, the boa data element. Now, this store has to be atomic in the sense that any concurrent reader has to be either the old value or the new value, not some mashed up of the two. So such a store would have to be carried out using a relaxed atomic variable. And you'll notice that the cat's next pointer continues referencing the GNU's data element to accommodate readers that are still referencing the cat. So from this point forward, there is no path to the cat's data element, indicated by the yellow color, okay? So new readers cannot gain access to it. Once the cat's reference counter reaches 0, then transitioning to state 3, the third column, all the readers that had a reference to the cat's data element have released their references, indicated by the boa's, indicated by the green color of the cat's box. So because there's still no path to the cat's data element, new readers still cannot gain any access, gain any reference to it. So it's now safe to transition to state 4 by freeing the late cat's data element. So I teased about the comparison between 4 common ways of doing this, and that's reader-writer blocks, reference counting, RCU, and hazard pointer. So the 3 of us have worked really hard to try to construct a table to kind of give you an overview of what the differences is. Is it just about performance? No, not really. You want to choose a solution depending on what properties of log-free programming you care about. So starting with the top, you have readers, okay? You'll see that RCU and hazard pointers are both fast and scalable, whereas reference counting and reader logs are slow and generally unscalable, okay? On the next one, the unreclaimed objects, RCU can be, now you'll see that there's no unreclaimed objects with reader-writer logs and reference counting. That's pretty good. Hazard pointers is pretty okay. It's bounded. But with RCU, it's unbounded. So because unclaimed objects RCU can be very large, but this gives it forward progress because you can always nail down all the memory. So that's why it's unbounded. The next one after that is traversal speed, okay? RCU, so what do we have here? With traversal speed, there's generally, a reader-writer log has generally no to low overhead, same with RCU, and hazard pointer generally has very low overhead. Whereas reference count, of course, is going to need an atomic read-modify write update. And this is, the reason for that is because hazard pointers has low or no overhead because put traversal, because the store and the load from cache can be just done just using the cache, okay? With reference counting, you have to do 2 atomic operations, especially if you're doing decast. Then you have 1 to increment the thread count on the pointer, then you have to increment the reference count, you have to go back to decrement the reference count, go back traversing, and then decrement the count on the node you came from, which is another 3. After that, you have what's called reference acquisition. Well, what this means is that you can acquire the reference or keep trying until you get it. Or if you fail, then that just means you go back to some previous point. Now, with hazard pointer, so what do we have here? Hazard pointers is conditional, whereas RCU is unconditional, and reader-writer log is unconditional, whereas reference counting can be either. It could be conditional or unconditional. And the reason is that with hazard pointers, the pointer may be already pointing to an already removed object, and the hazard pointer is already released, so you have to go back to some stable point. Okay? If you're linkless, if you're doing some sort of linked list with traversal, then RCU is good because you know you will get to something. Reader lock is just unconditional, and reference count depends on the use case. The contention is the part that is most interesting. There's no contention for RCU and hazard pointers, whereas the contention can be very high for reader-writer locks and reference counting. Automatic reclamation, of course, is the big thing. This is whether the algorithm automatically reclaims it. With reference count, they do. They automatically reclaims objects. But with reader-writer locks, RCU, and hazard, you actually have to call a cleanup function to do the reclamation. So how long does it take to do this reclamation timing? Well, it's pretty immediate with reader-writer lock and reference count, of course, and it's deferred because it's user control. And this deferred gives the user control as to when to do the cleanup, but it still can be very, very fast. There are two other things which is of theoretical interest, what's called non-blocking traversal and non-blocking reclamation, okay? This is basically about the idea of traversal forward progress, where RCU does really well, whereas reclamation forward progress, it does really well is really good for hazard pointers, because it's just a fixed number of hazard pointers, and you just go right through it. But in DCAS, that's a little more complicated, so that's why this table we find very useful in terms of giving you some idea about how they compare. All right, so I'm going to finish off with what else could be in TS2. What time how's my time? 5:02. You know what? I'm just going to give a quick overview of these two, and then I'm going to stop and give my co-author a chance to continue. Okay? So what else could be in TS2? There's also something called a high-level interface called Snapshot. That's in P0561. And it turns out to be essentially a high-level interface for reference counters, or RCU, or hazard pointers. And then there's also something called asymmetric fence in P1202. Okay, so what Snapshot is it gives you an easy to use deferred reclamation facility, applying only to a single object, which is intended to be based on either RCU or hazard pointers or reference counting. So it cannot replace either RCU or hazard pointers in general. So here the example, oops, I haven't changed it. Here the example, what you're trying to see is that this is a server class that handles requests using some config data and can receive new versions of that config data, like from a thread that polls the file system. And then each request is handled using the latest config data available when the request is handled. So updates don't affect requests, or that's already in flight. So there's no synchronization that's needed between any of these operations. Then there's an interface. I won't go through the interface. Asymmetric fences. Okay, so this one is pretty interesting too. So there are some types of concurrent algorithms that can be split into a common path and an uncommon path. Now, both of which requires fences or other operations with non-relaxed memory orders, so for correctness, for instance. So what they do is that on many platforms, it's possible to speed up the common path by adding an even stronger fence, stronger than memory order sequential consistency, down the uncommon path. So these facilities are now being used in increasing number in concurrency libraries, and we propose basically standardizing the asymmetric fence and incorporating them into the memory model. There's one more slide. I'm going to talk a little bit about the use of TS2 and how to use it safely. Okay. So this is pretty interesting. Now that you have all these tools in your toolbox, what do? It turns out that with deferred reclamation, this can be applied pretty easily to concurrent linked data structures. So with hazard pointers, it's not hard to convert reference counts to hazard pointers. There's no blocking concerns because reclamation objects are bounded. And because we are removing the cleanup interface in IS-26, your code should be aware of any dependencies on destructors. Now with RCU, this is also interesting. The readers might block reclamations if it's unbounded, so an unbounded amount of memory might remain unclaimed. But it turns out that if you're doing safety critical, memory is bounded anyway. And it's actually bounded by this formula that you see, I'm not going to repeat. But in safety, if you use static allocation, then you're not going to have new injections into your animal zoo you're not going to have any new injections. And that's actually good because it's not going to block reclamation. So if you recycle a fixed number of statically allocated blocks, then blocking in an RCU reader is less damaging to updates than blocking in a reader-writer blocking reader. Other thing is that an RCU reader typically only blocks recycling of memory, allowing updates to proceed concurrently with RCU readers. And in contrast, reader-writer locking readers blocks updates entirely. There's also a discussion about coroutines, which is now in C++ 20. And it's similar to things like student mutex. RCU readers should not span a coroutine suspension point unless you have used special non-standard extensions or use cases. I think Boost has one of those capabilities. And then similar to reference counting, hazard pointers, however, can be held across coroutine suspension points and further can be passed from one thread to another. Now, both hazard pointer and RCU do have debugging issues due to thread switching in a coroutine. Okay? And with that, I want to pass over to my colleague.
Thank you, Michael.
Thank you.
My mic is on. Thank you. Thank you, everybody, for being here. So mainly I'll talk about how can we use hazard pointer given the interface that we'll have in the near future in the TS2, or if things go as planned for C++ 26. So, but first I'll just very briefly describe what is, in case anybody likes to be self-contained, how does hazard pointer work? It's a big library, but it really boils down to a very small algorithm. And the algorithm is basically a hazard pointer is just a single pointer. It has a single owner and any number of readers. The owner can write to it. So if a hazard pointer is set to a value, it's basically saying, if this pointer, the object pointed to by this pointer has not been removed, so from some source, it's not accessible anymore, then it will not be reclaimed until this hazard pointer changes value. So that's kind of the basic algorithm. So if you look at, there are kind of two types of threads. There are the protectors who want to protect object or structures, but mainly object. They use hazard pointers to protect. And then on the other side, there are types of threads that remove objects from being reachable, and then they want to reclaim them. So the algorithm is just like the protector will set the hazard pointer to the object to be protected, and then check, has it been removed? If it has been removed, then okay, we have to retry, because there's no guarantee that it has been protected before it got removed, right? On the other side is okay, remove an object, and now we'll say, don't reclaim it until there are no more hazard pointers protecting it. That's it. That's the algorithm. It's fast, scalable. And also, because it protects specific objects, it can be held, protection can be held arbitrarily long, which that's a differentiator from RCU and reader-writer locks. Okay, moving on to the TS2 interface for hazard pointer. This is a very small font. We're not going to go through that. Just I want to put it in one slide. That's the TS2 interface. What's in bold is what we're proposing for C++ 26. So it's a proper subset of that. And in this talk, I'm going to talk about even a smaller subset of that. That's kind of an essential interface that I just want to show that it's quite useful even with this limited interface. And then we have a roadmap for extending that beyond 26. So I'm going to go through these and explain because that's the context for this part of the talk. So in the next slide, I'm going to get there. But basically, we have a class template for objects that are protectable by hazard pointers, and that's the hazard pointer obj base. And it just supports retire operation. And then there's the hazard pointer object themselves, and they control the actual hazard pointers that I talked about in that introductory slide. And it has like it can supports move operations. There are empty hazard pointer objects and so on. So let's go through that in kind of one-line description in most cases. So as I said, that's like the base type, the hazard pointer object base. That's the base type for protectable objects. The retire operation, it's intended to be used. It's called once, at most once in the lifetime of a protectable object, and it's if the user uses correctly, it's a already removed object, and it's passing the responsibility for reclaiming it to the library. It's saying, okay, I removed this, and now I'm giving it to the library to reclaim it whenever it's appropriate, where the library knows that there are no more hazard pointers protecting it. Now we look at the hazard pointer object type, and it supports like the default constructor constructs what we call an empty hazard pointer object. It's not associated with an actual hazard pointer. So it's just like it's used for moving from and to operations that I'm gonna get into in a few slides. There's also move operator and move constructor, and these are useful for very quickly transferring the ownership of an actual hazard pointer from one hazard pointer object to another. And I'll show examples of that. The destructor just releases the ownership of the hazard pointer and ends any protection associated with that. I should say about the move, the move to becomes as if it's like kind of released, and then if there's protection from a moved from, it continues. So we're not changing the protection from the hazard pointer, like as I showed, like protecting an object. It's actually continuing, because that's very important. It's like the protection it has to be continuous. The ways we use hazard pointer to protect objects, there are three operations: try protect, protect, and reset protection. Try protect is like, say, we give it a pointer and we give it an atomic source and say, try to protect that pointer, but then also protect it with a hazard pointer, and then double check that the source still points to it, because that tells us that it hasn't been removed. So if it hasn't been removed, then okay, by the conventions of the use and the specification, then we know that pointer from now on is protected until we end that protection. Okay. There's also a function called protect, which we use actually more commonly, where we say, here's a source, just get me a pointer that's protected. So it's kind of basically in a kind of simple implementation, it's just like kind of try protect, like reload a pointer from the source and then try to protect it until it succeeds. And reset protection is just saying we know that this is like not removed. So and if that's true, then start protecting now, and that will be honored by the library. There are two free functions. Make hazard pointer, it actually constructs a non-empty hazard pointer object, which is associated with an actual hazard pointer, and this is the one that can be used to actually protect objects. Where an empty, it's really it's an UB to like undefined behavior to call like try protect with an empty hazard pointer object. There's a swap operation to kind of like, you have two objects and now you're gonna swap the ownership of hazard pointers. So we'll see uses of these. Okay, so in this part of the talk, I'm gonna talk about three use cases, examples, and we'll just go see how this minimalist interface can be quite useful. And this is based on experience with the Facebook Foley library, and it's been 5 years of extensive use in production. So the first case is protecting access to an object, and that can be arbitrarily long or short, and very low overhead, fast, scalable, all this. So let's look at, this is the kind of, if you want to get just one use case of hazard pointer, this is it. So this is like the main use case. And basically you have an object type. In this case, we're going to say, okay, this is like going to be inherit from the base like template, which really supports retire. And here you have a frequently called operation to access or read the data. And there's an infrequent update. So in this case, let's look at the update first. The update is just like going to replace the object with another one. And then instead of reclaiming the object, it's just going to retire it. So that's it. That's the difference here. Let's look at the access. The access, okay, is going to create a non-empty hazard pointer. It's going to use that hazard pointer to protect an object that is accessible from the source. And once you get that protection, from now on, that object is protected as long as the hazard pointer, the non-empty hazard pointer is alive. And that's like the end of scope. And now we have a function that is user-defined. And this is where hazard pointer, this is the compelling case for it, is that it allows that function to be arbitrarily long or have dependencies. Because hazard pointer library doesn't introduce dependencies or prevent reclamation of other objects. So it's only protecting the objects that's specifically protecting. So it's not, that's why it's bounded number of objects that are unreclaimed. So this is the use case of that. All right. Let's move on to the second one, is hand-over-hand traversal. So this is using an example of a concurrent linked list. It has a single writer or multiple writers that are synchronized together. So it's like that's not our concern. Like when someone calls remove, they're actually already synchronized. So we treat them as if they're one writer at this point. There is a kind of a handshake between the writer and the readers, where it's in the slides. We can feel free to look at them when you look at the slides, but it's actually not our concern. It's about the traversal that we're going to get into the next slide. So just consider this: when the writer removes an object, there is a handshake there, and it nullifies the next pointer of the node and retires the node that it removed. So that's from the writer's point of view. From the readers, we want them to be fast and do hand-over-hand protection concurrently with the writer. So the writers need to do synchronization. The readers don't need to synchronize with each other or with the writer. In this case, again, no need to delve too deep into the protocol there between how they are confirming that the object is not removed or to proceed or not. But in this case, it's just let's look at how they are doing hand over hand. Is that we're just protecting two objects at a time, two nodes at a time. And in each iteration, so now there's a previous pointer and a current pointer. That's what hand over hand. And there's a hazard pointer for the previous and hazard pointer for the current. And then when we get through that loop and move on to the next iteration, we do a swap of the two hazard pointers. So it's actually for example, we're going from one iteration where there is a hazard pointer protecting, this one and the previous node and then the current node. But in the next iteration, the current becomes previous and the next becomes current. So actually, we are keeping, even though the name changes, Oh, sorry, I actually didn't mean to go to the next slide. Yeah, even though the name changes from current to previous, but it's actually the same protection. The protection is continuing for the same node. And now we're using what used to protect previous to try to protect the next current. So it's kind of hand-over-hand protection. There are kind of pitfalls. That's why I have the next slide. I kind of skipped ahead. So here it is. This is kind of an incorrect way of doing it. So it's just like if we don't do a swap of the hazard pointers, which swap will guarantee that the protection is continuing. We actually say, oh, let's just like use the previous hazard pointer to protect the next one, or like or kind of like move to the current and so no. The problem is any of these nodes could have been removed already, and if we start protecting them after being removed, then that violates the algorithm. The algorithm is saying you have to protect the object before it is removed. So we still need the swap. Okay, let's look at another pitfall here, or incorrect way of doing this, is say, okay, why do we need to swap? Why don't we just like, the previous hazard pointer is not used anymore, so let's just move into it the current. The problem is that we lose the hazard pointer for the current object becomes moved from. Then it's an empty. Then we can't use it to protect in the next iteration. So that's the second use case of hand over hand. Okay, the next one is iteration, and actually this is quite important. Basically, hazard pointers can be used to support iterators on concurrent containers. And why is that? And it supports that. Okay, it does not prevent progress by the updaters of the container, and it hands to the user an iterator that the user can hold on to for arbitrarily long time. So these are the advantages of hazard pointer, and they enable iteration that I don't think it's common in, I know that there are some libraries where the iterator holds a reader lock, or, that it prevents updates. And so let's look at this example, again, without delving too deep into the details of it, but it's like seeing how it is being used here. So let's say this is a hash table. For simplicity, just like a hash set. And you see the node here has like, a key and next pointer. I'm getting notification from Paul, so probably Michael follow that here. Okay, so let's look at the node. The node has key, and it has a link count to kind of guarantee that to protect the chain in a hash table bucket. It supports like acquiring link and releasing link, and when the link count goes to 0, then automatically we retire this object. And objects is going to be only when you retire a node, then only that you can retire the its descendants. So if you know that the node is alive or because you're protecting with a hazard pointer, it's actually, that you're protecting the next one. So in this case, this is like higher level code. It's not in the hazard pointer library. We're using the hazard pointer library. And we haven't gotten there yet, other than what you have seen in this using of the template and retire. If we look at the writer, again, it's just like, think of it, the writer is synchronized somehow. That's okay. When it removes a node, it's gonna bypass it. So now we have like the next node will have an extra link to it. So that's why we're acquiring the link. But then the target node, the node that we're removing, is gonna be releasing a link. So when we release the link, we potentially retire the node. So in the common case, it is retired. Okay, so let's move from, this is not like the meat of it. The next thing is going to go to look at the iterator itself. So now we have an iterator in this container. And the iterator rule, in this example, is a simplified one. It has two hazard pointers. It's for traversal. And I'll show how. But it's kind of like, so it's basically iterator pointing to a specific node that is like item in the hash table. Again, it has functions here to initialize the hazard pointers and a function to move on to the next node. And in this case, we know that, okay, we're protecting one node. We call protect on the next one. And actually, we know that we're protecting the whole linked list that are descendants of the current node. Okay, let's look at the main operation in iterator is the, I guess, the increment, if that's a proper name. And in this case, we are protecting the next node and swapping the two hazard pointers to kind of maintain the same naming, but without interfering with the protection. The protection is continuing. And we have a begin and end, so there's support for all this. You don't need to get into the details. Again, this is like just for completion, for completeness, there's this code, but it's about, okay, you could build iterators with this kind of minimal support for hazard pointer. Now let's get to the next slide, and that's like the last one in this example, is that this is user code. User code can just use this iterator as normally as you use C++ iterators of like, you start from begin and you end with the end and you increment the iterator. But just keep in mind that this is completely concurrent with updates, completely concurrent with each other. Like you can have hundreds of iteration operations going on concurrently. And the user can do whatever they want with the iterator. I mean, they can block. They can just hold on to the iterator and wait on a queue or something. That's fine. That's the ability that you can get from hazard pointer, the interface that we have proposed for TS2 and C+26. I will. Before I hand off to Paul in a minute or two, just I want to say that there's also a roadmap beyond 26, and that expands like hazard pointer to do synchronous reclamation. If you look at my talk from 2021, CppCon 21, about that, and also we can have link counting, different from the link counting that you saw in this example, where actually you can have integrated link counting that more optimal and these are extensions that don't take away from what we can do with it like today. And all these have been in production for 4 or 5 years in the Folly library in Facebook. Well, thank you, and I'll hand it off to Paul, hopefully remotely. All right.
Thank you, Magid. I'll hold off on video because we're intercontinental here, and I'm going to be cautious. So I'm going to talk about a stupid R2 trick. We'll see at the end of the slide set, there's a whole pile of other stupid tricks. If we go to the next slide, please. Okay, this is just a quick graphical introduction to RSU semantics based on the example that Michael Wong showed near the front of this. And so we have 4 different scenarios. As long as RSU synchronized waits for that reader to complete, as shown here. Because after RSU synchronized completes, the updater is probably going to free the old memory, and we want to be gone by then. If we go over to the upper write, we have the other way around. In this case, RSU synchronized started before the reader. The reader, therefore, has no access to the removed memory. The open curly brace and a closed curly brace. And it's okay if, which means that the read from the linked data structure, it's okay to read. The lower suspenders example, the reader wasn't around before they are synchronized, therefore the reader can't possibly have access to removed data, and at the same time it was gone before the stuff was freed anyway, so it's doubly protected. The lower right would be a bug in RCU, all right? If you have a reader that's
I could continue the talk on behalf of Paul, or if that's okay. Just don't judge me harshly. Yeah. Okay, so I think this slide is about like looking at different timings of RCU reader protection and then removal and then calling RCU synchronized. So these three make sense, but the fourth one doesn't make sense because there's no way that synchronized will succeed while holding a reader lock. So it's kind of like protect, just a background RCU reader saying, okay, I want to protect everything in this section. Don't reclaim things that haven't been reclaimed earlier. So synchronized is kind of like saying, okay, anything that was reclaimed, that was removed after I start, then don't reclaim them. Wait for it. Wait for these reader sections to be done. I think Paul is meant to show like there are many tricks there associated with the RCU, and he's going to focus on phase state change. And here said it's a low-level primitive known for RCU's case. It's in multi-thread application. Flag to indicate that care is required. So it's kind of like, it's a common case where you can be fast, but then there's kind of like rare cases where you need to do something extra to be careful. So you don't want to spend too much like time regularly being careful when we don't need to, but then when we need to be careful, we really have to be careful. So that's kind of like the use case that Paul had in mind. Phased state change. Okay, so so it's kind of like normally you can be quick, but then just like before the maintenance period, you can be either quick or careful. But then in the maintenance period, you really have to be careful, and then there's a period where you could be either, and then in the steady state, be really fast. So this is the kind of common case operation. You would have an atomic bool that says "be careful," and mostly it's going to be false. So with the kind of low overhead, in a way, you can say, okay, if "be careful" load is false, so in the common case it's false. So you're paying the overhead of checking that bool. So that's kind of like, and it's a relaxed order. But if you need to be careful, then of course you pay the price, and that's okay. Okay, so let's look at this. Then the maintenance operation, this is where the protocol is to, you say, okay, be careful, and then you do RCU synchronize, and then you do the maintenance, and then you do another RCU synchronize, and then you say, don't need to be careful anymore, and these are all relaxed. So like the goal is, the goal is to make the common case as lowest overhead as possible to be like relaxed load of a bool. That's kind of the goal here. And this is like the maintenance operation. You do that to, and Paul is asking, why is this needed? Why RCU synchronize needed again? And in this slide, so okay, what if we don't do the RCU synchronize? Then the store, the store to be careful to say don't need to be careful might actually overlap with the maintenance because it's relaxed. Then that's bad, and yeah, then that's why that's bad. The other alternative is to not do another RCU synchronized, but then now you need release acquire kind of order, which in some platforms that's like adds some cost that this case is trying to avoid. So if we say that the store to be careful has release order to guarantee that the maintenance completed, then in the common case, you need to use load acquire. So these are kind of like the trade-offs, and that's the trick that Paul wanted to share with us. I'm sure Paul would have done a much better job explaining this, but yeah, so it's almost like it's near zero common case read side synchronization overhead, maybe load acquire, and in case you want to save this RCU synchronize extra. So this is a pattern that's used in the Linux kernel, and I don't know if Paul is sending me a smiley face or a frowning face. It's hard to tell, but I'll assume it's a good one. So. Yeah, and it's one trick of many, and Paul leaves us with many tricks to look up in these references. And this actually concludes our talk. And if you have any questions for Michael and Ian or Paul, I'd be happy to answer your questions. Thank you.
Great talk, and good to see it all coming together. From a folly perspective. From a folly perspective.
Thank you.
How close or how far ahead is what I would find if I went and forked the current trunk on GitHub to either TS2 or IS?
Right. Very, very good. Yeah. Folly is a superset of all this and more. So it's actually even the things that, so I mean, I'll give you an example is like synchronous reclamation is actually, we shifted, like that's long ago shifted from global cleanup where, say, just clean up everything, and now it became like focused. We actually support both, like because we want to keep like TS2, it's fully supported, but also the newer features, which, I mean, they're not new anymore, they're at least 4 years in heavy production use. So yeah, it's a superset. I mentioned a few, so like, yeah, the C++26 proposal is there, fully supported, fully in use in like, since 2017. So that interface is quite stable. The TS2, again, all of it from 2017 at least. The things beyond that, synchronous reclamation, 2018, integrated link counting, 2017. There are some optimizations that are like, arrays of hazard pointers. It's like, why would we pay the cost of, I mean, there are a few nanoseconds of thread local, that why not pay that once for the whole. So anyway, these are all there. So long-winded way of saying, yes, it's all in folly.
Thank you.
All right. Okay. Thank you, everyone. Okay.